All right, before we jump into the solution, let's clearly understand what the question is asking. We're given an array called nums. We're allowed to perform one operation any number of times. In one operation, we look at all adjacent pairs in the array, find the pair with the minimum sum, and if there are multiple such pairs, we always choose the leftmost one. Then we remove those two elements and replace them with their sum. Our goal is to find the minimum number of such operations required to make the array non-decreasing. Non-decreasing simply means every element should be greater than or equal to the previous one. Let's understand this with an example. For the array 5, 2, 3, 1, the adjacent sums are 5 plus 2 equals 7, 2 plus 3 equals 5, and 3 plus 1 equals 4. The minimum sum is 4, so we are forced to merge the pair 3, 1. After merging, the array becomes 5, 2, 4. Now again, the minimum adjacent sum is 2, 4, which gives 6. After merging that pair, the array becomes 5, 6. At this point, the array is non-decreasing, so the answer is 2 operations. In another example, 1, 2, 2, the array is already non-decreasing, so the answer is 0. Now here comes the most important part. How do we approach this problem? The key thing to notice is we do not get to choose which pair to merge. At every step, the problem strictly forces us to merge the adjacent pair with the minimum sum. So this is not a greedy problem where we pick what looks good. Instead, our job is to efficiently simulate these forced merges without doing it naively. A direct simulation would be too slow because the array can have up to 100,000 elements. So our approach is this. We use a min heap to always know which adjacent pair has the minimum sum, and a doubly linked list to merge and update neighbors efficiently. The heap decides what to merge, and the linked list decides where to merge. With this combination, we can process all merges efficiently and stop as soon as the array becomes non-decreasing.
Step 1. Node definition. Linked list. Let's start by defining a node. Each number in the array becomes a node in a doubly linked list. Why a linked list? Because after a merge, elements disappear and new ones appear, and shifting arrays would be far too slow. Each node stores its value, a pointer to the previous node, a pointer to the next node, and one important flag called alive. That alive flag helps us ignore outdated pairs later. Step 2. Adjacent pair definition, heap element. Next, we define what goes into our heap. Each heap entry represents an adjacent pair. It stores the sum of the two numbers, the left node and the right node. This heap is always ordered by sum, so whenever we pull from it, we get the exact pair that the problem forces us to merge. Step 3. Method signature and edge case. Now we move to the main function. If the array has 0 or 1 element, it's already sorted, so we immediately return 0 operations. Simple, clean, no unnecessary work. Step 4. Build the doubly linked list. Now we convert the array into a doubly linked list. Each number becomes a node. We carefully link every node to its left and right neighbors. This preserves the original order and allows us to remove or insert elements in constant time. Step 5. Build the min heap of adjacent pairs. Once the list is ready, we build the heap. For every adjacent pair in the list, we calculate their sum and push it into the min heap. At this point, the heap knows all possible merge candidates. And from now on, the heap decides which pair must be merged next. Step 6. Operation counter. We also keep a simple counter. Every time we merge two elements, we increment this counter. At the end, this is our answer. Step 7. Main merge loop. Now comes the heart of the solution. We start a loop that keeps running until the array becomes non-decreasing. Inside this loop, we repeatedly apply the forced minimum sum merge. Step 8. Check if the list is sorted. Before performing any merge, we check if the list is already non-decreasing. We walk through the linked list from left to right. If we ever see a value greater than the next one, the array is not sorted yet. But if we reach the end without finding such a case, we immediately stop, because the problem asks for the minimum number of operations. Step 9. Extract a valid minimum sum pair. Now we pull from the heap. But here's the tricky part. Some heap entries are outdated because their nodes were already merged earlier. So we keep popping until we find a pair that is still alive, still adjacent, and still valid. This technique is called lazy deletion. It keeps the algorithm fast and clean. Step 10. Merge the pair. Once we have a valid pair, we perform the merge. The two nodes are replaced by a new node whose value is their sum. This is exactly what the problem statement tells us to do. And yes, this merge is forced. We never make a choice here. Step 11. Relink the neighbors. Now we update the linked list. We remove the two old nodes. We connect the new merged node to the previous neighbor on the left and the next neighbor on the right. Then we mark the old nodes as no longer alive. Step 12. Push new adjacent pairs into the heap. After the merge, only the new boundaries can form new adjacent pairs. So we push the pair formed with the left neighbor and the pair formed with the right neighbor. Everything else in the heap remains untouched. Step 13. End loop and return result. We repeat this process until the array becomes sorted. Finally, we return the total number of merge operations. That's it.